Hi class, Mrs. Thomas here. So in our last video, we talked about factoring. You do need to have a general understanding of factoring in order for today's lesson to make sense. So today's lesson, we're going to talk about factoring, factoring different kinds of polynomials that aren't necessarily quadratics. All right, so what we're going to do is focus on polynomials or trinomials that are of the form ax to the power 2n. So instead of it being ax squared, it could be a even number of anything as long as our middle term is bx to the power n, right? So this term is going to have a exponent that is twice that of the middle term, and then plus c. So whenever we see a trinomial of this form, we can actually factor it using the same methods as quadratics. Just going to focus the camera. There we go. So we can factor using quadratic factoring methods. So what do I mean by that? Let's look at some examples, right? So my first example that I'd like to show you is x to the power 4 minus 12x squared plus 20. So if I were to ignore that this was to the power 4 and that this was the power 2, right? Like let's say this was just x squared minus 12x plus 20. I would go about factoring this using product sum method, right? So I have product of 20, a sum of negative 12, and since my a value is 1, right? If this was my a over here, I've got an a value of 1, my b value is negative 12, and my c value is 20, right? Using my quadratic form over here. Since my a value is 1, I can actually factor this as if it was a simple trinomial, right? So if I were to factor this as if it was a simple trinomial, well, a product of 20 and a sum of negative 12, I have, I can go through all the different factors that multiply to 20. I can find that negative 2 and negative 10 will multiply to 20 and add to negative 12. And then I'm going to factor this out. So I would factor it out and get an x squared minus 2, which is my first factor, times x squared minus 10, my second factor. And the reason why I'm using x squared is because x squared times x squared is going to equal x to the power 4. Right? So if I were to expand all of this out, I would get x to the power 4 minus 2x squared minus 10x squared, which would add up to minus 12x squared, and negative 2 times negative 10, which is plus 20. And similarly, let's look at another example that's very similar to this one, only instead of it being x to the power 4, let's say it's x to the 6. Minus 12x to the 3 plus 20. So notice that my exponent in the first term is twice that of my exponent in the second term. And that's what I meant when I was saying ax to the 2n. So let's say my n was 3. Ax to the 2n would be x to the 6, right? And bx to the n would just be negative 12x cubed, right? So since this has the same product and sum as in the first example, it also has the same factors, negative 2 and negative 10, multiply to positive 20, negative 2 minus 10, add to negative 12. So it's the same idea here. So I have a product of 20, a sum of negative 12, negative 2 and negative 10. And the only thing that really changes as I am factoring this is instead of it being x squared minus 2, I'm doing x cubed minus 2 times x cubed minus 10, because x cubed times x cubed is going to equal x to the power 6. So next, let's look at some more examples of more complicated factoring. And what I'd like to focus on for the rest of this video is different examples of differences of squares, right? So if we remember from our last lesson, a difference of squares is whenever we have a square one term minus the square of another term, right? So if you remember, this was a difference of squares, right? But it doesn't always look obvious like a difference of squares. So let's first look at something that isn't necessarily a square. So let's look at an example of a to the 4 minus b to the 4. If you remember in our last lesson, whenever we have even exponents mean a square, right? So a to the 4, well, the square root of a to the 4 is a squared. And the square root of b to the 4 is b squared. So if I'm factoring a to the 4 minus b to the 4, I'm going to have a squared plus b squared times a squared minus b squared. And once this is factored, I need to look at my factored terms and I need to decide if they are also factored, right? So a squared plus b squared, I can't really factor that anymore, but a squared minus b squared, well, that satisfies a difference of squares. So I can actually factor this term again. So I'd be left with a squared plus b squared, that just transfers over, and then I'm going to have something plus something times something minus something. And the square root of a squared is a, so that's my first term, and the square root of the second term is b, and that's my second term. So this has actually now been factored completely. So we always have to be careful when we're factoring something to check if we can continue factoring as well. Let's look at some more examples of difference of squares. So let's look at the example of 4 times a plus b squared minus c squared. So we're on example D. So this is example D. Just going to check to make sure we're still in focus. There we go. So I have, we can ignore this bracket. So I have 4 times a plus b squared minus c squared. Now, this is actually a binomial. I have a term here, and I have a term here. So 4 times a plus b squared, if I were to take the square root of that, I'd be left with 2 times a plus b, right? Because 2 times a plus b, right? If I were to square that, 2 times a plus b times 2 times a plus b is the same as 2 times 2, which is equal to 4, and a plus b times a plus b, which is a plus b squared, right? So the square root of this first term is actually 2 times a plus b. Square root of the second term is a little more straightforward. We've got a c squared. So the square root of that one is just c. So when I'm factoring this, I'm going to be left with 2 times a plus b plus c times 2 times a plus b minus c. Now we can leave it this way, or if you would like, you can also expand it out. So you can get 2a plus 2b plus c times 2a plus 2b minus c. So let's try more difference of squares that look kind of weird like this. So let's try 9a minus 2b squared minus 3a plus c squared. And the reason why we do this is because it's really important that we start seeing as many examples of difference of squares as we can so that we learn how to recognize them, right? So dead giveaways that these are squares is first we can see that there's an actual 2 in the exponent. We have an even exponent, right? So as soon as we see that even exponent, that's kind of a big clue that this might be a square. And then we also have this 9 in front, and 9 is also a square. So if I were to take the square root of this first term, square root of 9 times a minus 2b squared is the square root of the number, which is 3, and the square root of this binomial, which has been squared, is just the binomial, right? And the square root of the second term, since it's been squared, is just the term by itself, right? If I take the square root of a square, it cancels out the square, so I'm left with 3a plus c. And then factoring this just becomes a matter of writing out those terms. Plus 3a plus c times 3a minus 2b minus 3a plus c. I do recommend keeping your terms in brackets whenever possible like this, right? The square root of 3a plus c squared is still in brackets, and the reason why I recommend doing that is so that we don't accidentally forget about that negative, right? So if I want to remove the brackets, if I want to expand it out, I will be left with 3a minus 6b, right? Because 3 times a is 3a, 3 times minus 2b is minus 6b, and here it's just positive 1 times everything inside the brackets, so it doesn't change anything in this one. But it does change something in our second one. So 3 times a minus 2b is 3a minus 6b. And then minus 3a plus c will be minus 3a minus c. Okay, let's look at one last example. And that is an example of something that isn't a trinomial. So let's say we have 16x to the 4 minus y squared minus 10y minus 25. So let's say I have something that is more than 3 terms. So if you remember from the last video, whenever we have something that's more than 3 terms, that means we need to look into factoring by grouping, right? So since we have 4 terms, seems like my pen is running out of ink, so I'm just going to write it in red. If we have 4 terms, look into factoring by grouping. So we looked at factoring and grouping by combining the first 2 terms and factoring them, and then combining the second 2 terms and factoring them. And it does look like there are things in common in our first 2 terms and things in common in our second 2 terms. But something else that kind of jumps out at me, especially after all that practice with perfect squares, is that we have this perfect square over here, right? So what I mean by that is that if I were to factor out a negative 1, I have y squared plus 10y plus 25, right? And that means I have y, which has been squared to make y squared. I have a 5, which is squared to make 25. And then my middle term is 2 times y times 5, which is 10y. So since I have this perfect square here, I can actually rewrite it as a square. So I have y plus 5 squared. And now I have a difference of squares, right? So I have the square root of 16x to the 4, which is 4x squared. And I have a square root of y plus 5 squared, which is just y plus 5. And I can factor this out as a difference of squares. Let's make a little barrier. So I've got 4x squared plus y plus 5 times 4x squared minus y plus 5. So if you want to get rid of your brackets, you can also do that. Times 4x squared minus y minus 5. And that is a completely factored 4-term polynomial. All right, so your homework for tonight is on page 102, number 1 to 9. So it's on page 102, numbers 1 to 9. You can just do A and B for each one and give, although if you do need more practice, there are more questions available in your textbook as well. Happy factoring, everyone.